As you already know, this is a solar panel. You also know that solar panels offer a great advantage over fossil fuels. They provide us with a less carbon-intensive path towards electricity. Despite such an advantage, the uptake in solar panels has not met the expectations. That is because the current solar technology, which is made of silicon, has proved to be financially challenging for the past 40 years and has been relying majorly on government subsidy for consumer uptake. To understand this problem better, I want to show you a quick analysis. The process to make silicon solar panels starts with piling up sand and then melting it using really high temperatures. This is the most energy exhaustive step of the process. Then from the molten sand, we create single individual silicon cells. And as for the final step of the process, we bring all of these individual cells together and assemble them into a module. Up until this point in the process, we have generated about 55 grams of carbon dioxide, which means to balance that out, we'd have to take that module and run it nonstop for 5 years. This is what we call the payback period. And as far as the payback period goes, this is considered to be a very good number. Unfortunately, however, this is not the end of this analysis, and there's one more aspect to consider. A solar cell manufacturer has different sources of cost to cover, from materials to equipment and maintenance. Which means that if I were to agglomerate the carbon dioxide analysis and the cost analysis, I'd be looking into realistic payback periods as long as 10 years. I want to bring this to your attention that the expected lifetime of silicon solar panels is about 20 years, which means by the time that you're done paying off the carbon debt and offsetting the profit margin, half the lifetime of your solar panel has already passed. So now you understand that despite being a very promising technology, silicon solar panels are associated with high amounts of emitted carbon dioxide and manufacturing costs. But here's the thing. What if we could keep utilizing solar technology as a path to produce electricity, but rather benefit from a lower carbon footprint and manufacturing costs at the same time? Well, I'm here today to tell you that that is in fact possible through utilizing perovskite solar cells. However, while perovskite solar cells and silicon solar cells start off with the same number of efficiency for converting sunlight into electricity, after a while, and because of some processes that happen during the operation of perovskite solar cells, their efficiency values start to decrease until the cell goes fully offline in about 24 months. Before I tell you why the things happen, let me bring some material science into this. Perovskite solar cells are made from a few different layers, with each layer serving a very distinct purpose. At the heart of the solar cell, we have the perovskite layer, which is arguably the most important one because it can absorb the sunlight and break it down into a currency that the system is able to spend later to generate electricity. This currency is the positive and negative charge. So far, we understand that these solar cells get their name from their absorber layer. And now the question is, where does the absorber layer get its name from? Perovskite is the name of a crystal structure, or in other words, how the elements line up with respect to each other on the atomic level. When perovskite technology first started, the composition had only methylammonium, lead, and iodide. And now, after 10 years of constant development to render efficiencies competitive with silicon, the composition is way more complicated than that. This is something that I'll get back to later when I explain my research. But for now, let me show you how these solar cells actually function. When this cell is sitting in a dark room, nothing is really happening. We still have the positive and negative charges that I told you about, but they're sitting still because they have no energy. But we can change that by placing that solar cell under the sunlight. Because now, like I told you before, the perovskite layer is going to absorb the sunlight, and the positive and negative charges that were sitting still suddenly gain enough kinetic energy to move as far away from each other as possible. This is where the capability of the perovskite layer ends. Now we need 2 new layers that are capable of transporting these charges. For that reason, we have the negative transport layer to transport the negative charges, and the positive transport layer to transport the positive charges. We also have the metal contact to extract the positive charge, and the base layer to extract the negative charge out of the solar cell. So now that you know how the solar cells actually function, let's go back to the separated positive and negative charge and see what actually happens to them. In an ideal case, these charges are going to get transported through all of these layers really fast, go in the outer circuit, recombine, and give us electricity. However, in reality, things are a little bit different. We still end up separating the positive and negative charge and sending them off to the respective transport layers. However, we will not be able to transport them through all of these layers in the timescales that we are interested in. To understand why, let me bring up the perovskite crystal structure again and remind you that we have a few different elements involved here, which means when the sunlight comes in, positive and negative charges are not going to be the only moving species. We'll also have the positive and negative elements that will get a kick from the sun and start moving around until they reside right behind the lineup of charges that are waiting so impatiently to get out of the system. As a result of this accumulation, these elements are going to apply some attraction forces on the charges and in essence trap them in their place. This explains why the charges are unable to get out of the system in fast timescales. This situation is a little bit less severe for positive charges, because after a few rounds of trying, they finally manage to get themselves in the positive transport layer and eventually the outer circuit. However, for negative charges, the struggle is real. They're going to have to try for much longer before they can finally get themselves into the respective transport layer, the base layer, and eventually the outer circuit. This delay that is associated with the transport of negative charge is essentially the root cause of the problem, because the charges that are trapped at the interface of the perovskite layer and the negative transport layer against their will are going to retaliate by causing some electrochemical reactions and therefore degrading the entire perovskite solar cell structure in about 24 months. What I'm focused on is making a negative transport layer that acts as a highway for the charges and enables them to get out of the system as fast as possible. Let me show you what I do in the lab to achieve that goal. I start off with a piece of conductive glass as my base layer, and then using some high temperature and high pressure processes, I make these rod-like structures on a nanometer scale, or as we call them, nanorods. Then I infiltrate these very small structures with a perovskite layer, and to finish things up, I deposit the positive transport layer. Now, I want to dive a little bit deeper in my research here. In a more detailed view, I'm interested in how playing around with the length of these nanorods can actually affect the performance of the resulting solar cell. And to understand that, I measure some parameters. And naturally, the first thing I look at is the stability. What I discovered was that the stability of perovskite solar cells based on longer nanorods tend to be higher, which is encouraging. But I also measured the efficiency and realized that it does not necessarily follow the same trend as stability. But my research can help us with understanding that. So the first thing that I want to show you is the interface between the negative transport layer and the base layer. Longer nanorods tend to cover the base layer better, which means that they do a better job at preventing the perovskite layer from directly touching the base layer. Now that is important because the charges that tried so hard to untrap themselves from the perovskite layer will have to go through the negative transport layer first before entering the base layer, or we are going to lose them. And if we lose them, they will not be able to contribute to making electricity. There is one more aspect to this. When light enters each one of these structures, it is going to have a limited number of interactions before it finally manages to escape. The number of interactions that light has with solar cells based on longer nanorods tend to be higher. This is because there are more surfaces to bounce off of. This essentially means that we are trapping the light and then recycling it over and over again, and as a result creating more charges. But this by itself creates a big question. Why does the solar cell that gives us the best coverage and the best light trapping properties still does not yield the best efficiency? To understand that, let's take a step back. And remember the most important parameter associated with perovskite solar cells. They tend to trap the charge at the interface and make it difficult for them to get out, which is why we measure a very important parameter called resistance, which tells us how resistant a certain negative transport layer is towards the transport of negative charges. What we discovered was that while a negative transport layer might be excellent at trapping the light and covering the base layer, it might not necessarily be the best choice for providing the charges with the fastest route out of the system. So far, I've been telling you about my efforts with regards to optimizing the negative transport layer. Now let me show you what I've been doing about the perovskite layer. When it comes comes to this layer, I'm interested in how I can fix the composition, but vary the deposition method, or fix the deposition method, but vary the composition to possibly tailor and fine-tune the properties of the resulting perovskite solar cell. And what we discovered was that the composition that you're looking at right now has superior properties in terms of both efficiency and stability over every other composition that we have tried so far. Today, I've been telling you how through utilizing perovskite technology, we have this opportunity to reduce the carbon footprint and manufacturing costs of solar cells. Fortunately for us, there is one more aspect to this good story. Perovskite solar cells are projected to overtake silicon and reach efficiencies of 30% and beyond in the near future. With increased efficiency, decreased manufacturing costs, and decreased carbon footprint, as a consumer, you'll be looking into payback periods as low as 5 years for perovskites, as opposed to 10 years for silicon, which means anybody who wants to purchase an efficient solar panel will not be discouraged by looking at the price tag anymore. Thank you. Oh, I know something I did wrong. Something I did wrong, or oh, oh God, I was dying. Like, thank you. Sure. Thank you. How long was it? I would say so. Yeah. Thank you.